The first task that we'll be doing is making the logic expression from the logic circuit. Forget what the activity says, we'll be utilizing the same activities for our purpose. Expression, as expression is the basis of everything in the questions, the type of questions we come across in the exam. So we'll be making logic expression. Starting from the part A, I'll be making right here. For the logic expression to be made, we need to have logic expression of individual gates, and there are two gates. The upper one is to focus on the inputs. We have input A, and then the input B going up in the AND gate. Okay, so we have this output, as A and B. All right, we can bracket them up. Then coming down, we need to have the output of this wire that will be going into the final gate, the OR gate. This is the final last gate. So we need to have this input wire, and we need to have information of this input. Only then we can have question mark or question mark, which will be equal to this X. Okay, so we need to resolve the question marks input. This input is A or B. I know this is pretty easy, and I just want to keep it as it is, and we'll be practicing a little more questions. A or B, packet them up. Then the same input A or B is negated after the NOT gate, and it will be not of the whole previous, which is A or B. Okay, so we have information on this wire, information on this wire. We can write the expression for the final X, and X will be X is equal to A or B from the upper input. It is read as up, center, down. The upper input, A or B. Up, the center is the name of the gate, which is OR gate. This OR gate, okay. This center gate OR. Then down here we have not of A or B, okay. And I put it wrong there. This is A and B. The upper input is A and B, or not of A or B. Okay, so there goes the expression for X. The B part is a bit trickier, or it should not be, but students are confused. You need to be writing these expression as it is, and you cannot have plus in replacement of or. Yes, it is, but you are not allowed to use plus dot for the and you should be writing the expression as it is in the English words, everything in the English words. Okay, moving to the part C, that is pretty fair and easy. Why C? Okay, you should be trying for B. As a homework, I'll be giving you the homework. So this up, center, down of this gate, the up is this input, down is the pretty simple, that is C, but we need to resolve the upper input. And for the upper input, we need to have the output of this XOR gate, and this XOR gate as an input of this gate, and then this gate. So we must be starting from these two gate. Why? Because these have direct connections with the input. Until you reach to a gate or gates that have direct connections with the input, you cannot start the making of an expression. Okay, so yeah, this is the question mark we need to resolve up first, because this is the simple C input to the X gate. Okay, so this is A or B, then bottom one is A, not of AND is N A N D, B, A and B, as both of the inputs are now there to be going to the XOR, so we can have question mark is equal to A or B. A or B, up, upper input, there it goes, up, Center is the XOR gate, XOR up center, and then down, which is A NAND B. This is the down input, and it is having A NAND B.
Sir, shouldn't it be B and C?
Okay, yeah, my mistake. Thank you. B NAND C. And now we have whole of the per input available to the final X gate, which is the whole expression we just made. And now we can write the expression for the last X or X gate, which is X is equal to the whole of upper A or B X or B NAND C or and C, right? You should be trying up the part B at least. I'll be giving you the homework, and the B part is one of the mandatory ones. I'll be checking it in the class on Tuesday. Okay, so make sure you do practice the B. This category of question is there in your final exam too, making an expression from the given logic circuit. Okay, then we should be moving. Any question from here?
Sir, aren't we gonna put brackets around A or before A or B and then
And
after
yeah,
B and
the
C?
bracketizing the whole one, we do not need to. We do not need to
Yeah,
because
okay.
okay. Yes, to prioritize this as a single input. Yes. To prioritize, you can even leave them open, but it is better to prioritize that this is a single input to the final X at the final OR gate, which is labeled as X. We should be putting these two brackets more. Okay. Should we move to the second category of question?
Yeah, sure.
Okay. Second category is making up the logic circuit from the expression, and we have activity. It was 10.4. Okay. So I'll be moving for option C. Okay, then you can try on your own the part E. For the C, we need to come up with a Boolean expression involving only the variables, whether they are on or off. So we need to eliminate the English switch K is on. Okay, so this should be written as if anything is on, that is just that variable. If K is on, it's simply the K. Okay, then it says or, and we have an OR gate. Switch L is on, so it will be simple L. Okay, K or L. Then we have this OR translated as exactly O. Switch K is on, the bracket starting K is on is written as K, and switch M is off, and goes exactly like A N T. Switch M is off, and that is written as not M, never M not. Why never M not? Because you always write -5 instead of writing 5 minus. So not gate is just like the negative, not is just like the negative in the mathematical regular algebra. In the Boolean algebra, the NOT gate is equivalent to the negative. So negative is always written prior to the number or prior to the expression before -5, not 5 minus. So this would be K and not M, but not K and M not. Okay, K and not M only. Closing the bracket. Then it says or, and then we can write or after the first two expressions. M is on, and that is written as M. Okay. Similarly, I can have you the expression for switch A is on, that goes for A, and N goes for and. B is on, A and B, and then the central gate, and B is on or switch C is off. B is on goes for B, or there is an OR gate in the center, or C is off, not C. Okay, both those expressions solved. Any confusion? So both of them are kind of similar. Okay, and they should be coming up the expressions like in D and B and A. Okay, so these expressions boiled up to just like expressions in the part A, B, and D. Fine. So moving for the expression C, the expression for the part C, and I'll be splitting up the display into half. Yeah. The first step in making the circuit is to label the inputs. Label or come up with the inputs that are unique. So we have inputs K, L, and M. K, L, and M. Coming up with the unique inputs, the variety of inputs, and that are K, L, and M. So we should be labeling K, L, and M. The first step. The second step is to put NOT gates where required. Second step is to put NOT gates where required, and there is only M that is requiring. There is only M input that is requiring a NOT gate. So
Sir, I have a question.
yeah,
सर अगर हम एंड लगाएं, सपोज करें ए एंड बी पर एंड लगाएं एंड देन हम उसके ऊपर नॉट लगाएं, या हम नैंड लगाएं, तो आउटपुट में डिफरेंस आता है?
हाँ जी बिल्कुल, ये यू कैन मेक अ ट्रुथ टेबल फॉर A and B. Okay, and then you want to not of A and B. You can try this whether this is equivalent to A NAND B. Okay. I also have forgotten whether they were equal or not. We can try them up. Okay. We can try them up right now. 0 0 0 1 1 0 1 1. No, sorry. This is the label for the A and B. So AB goes there 0 0 0 1 1 0 1 1. So 0 dot 0 is 0, 0 dot 1 is 0 0, and AND gate is only 1 when both of the inputs are 1. Okay, the inverse of this, I guess this will be same. 1 1 0, yeah, this both will be same. 1 1 0 will be the inverse of A dot B, and okay, and then doing the direct NAND operation on the inputs. So NAND is if any of the input if both of the inputs are on, then this will be 0, otherwise it will be 1. Okay, so this is how you prove it. You might come up with a question where you need to prove that the expression on the left is equal to the expression on the right. So only way to prove is to draw the truth table, and if the x columns, the output columns, the last columns match up, they are literally the same, otherwise not. Question cleared?
Yes sir, thank you.
Welcome. The first step was to list the unique inputs in the same sequence as the sequence in ABC. ABC, PQR, KLM, XYZ. Okay, then putting the NOT gates where required and only M input in the expression on the right of for the part C we made up. The come up involves NOT gate only M input. Okay, then drawing up the wires for the normal inputs. Okay, and how much length of wire? The same length of wire as for the NOT gate. Okay, so should be keeping care of so that the circuit is neat and tidy. Okay, then we need to make up the um, combinations as told by the brackets on the left hand screen. Look at the screen on the left hand side on the book. This says K or L. We need to draw up the gate for the K or L, and OR is the OR gate, and OR gate goes like K or L. So we should be drawing up in the center here the gate, the K, the OR gate. This is OR of okay, K or L, and you should be coming over the output wire, a little output wire. Then the second bracket, the bracket that is K and not M. K and not M are further apart by the L. So either we can draw up, we should be drawing up the AND gate for the K and not M exactly here. Why exactly here? Because both of the bracket to the OR, look up on the left screen, both of the brackets to the or are on the same precedence or on the same priority, because K or L is the left hand side of the OR gate and K and not M is the right hand side of the OR gate. Both are on the same level of priority or precedence. So both of the gates, the OR and AND, should be on the same level. Okay. drawing up the lines or connecting up the gates with the inputs K, and it says not M can be taken from here. Okay, so what did I try to do? Both of the inputs should be in the center of the gate. Both of the inputs should be in the center of the gate. Okay, and gate should be a little bit more bigger than the usual, like this. This bracket done, this bracket done on the left hand of the book, and then we need to patch them up in the center of both of those, OR gate, a little output wire, this and this. Both inputs in the center of the OR gate, and OR gate with the M can go into the center of the circuit like this, and M goes from the back of the NOT gate, back of the NOT gate, back of the NOT gate. Please focus on this. This is the back of the NOT gate. This is M, and after the NOT gate, here, this is M NOT, okay, or not M. So we require a simple M input. So we'll be taking it prior to the AND gate. Any question? And this is the output wire, and we were drawing this expression for T, labeling it as T. Any question?
No, sir.
Okay. We should now be moving to the last step, which is drawing up the trace table. Okay. So we should be going for the trace table of this exact circuit. Now it should not matter whether it is a circuit or whether it is an expression to draw up the trace table. It should not matter because this circuit belongs to an expression, and the truth table that we will be doing down here belongs to this circuit, and this circuit belongs to the expression. The truth table belongs to both expression and the circuit. Okay, drawing up the truth table from an expression or the circuit should not be a problem, because you can come up with an expression from the circuit and then you can start making the truth table. Okay. So you are already given with the input sequence. So input sequence is K, M, and M. That goes first input half time zeros, half time 1. Half time of what? 2 raised to power. Number of inputs 3 is equal to 8. Half of 8 is 4. So that goes for the first column, 4 times zeros, 4 times 1. Then half of the first column, 4 is 2, 2 times zeros. L is 2 times zeros, 2 times 1, 2 times zeros, 2 times 1. And the last is half of 2, half of the previous column, 0, 1. All right. Now we need to do what? We need to trace the table for each of the bracket K or L, then K and not M, then a disjunction of both of them, OR gate. Is it disjunction OR gate? Okay, I don't know the proper name for the OR gate. Drawing up the brackets for K or L. We also need to have not M, and not M is opposite of M, which is 1, 0. All right. Now filling up the brackets K or L. K or L. K is the most left column, and then adjacent to it is the L column. OR gate says OR gate will have an output of 1 if any of the inputs will be 1. So here both of the inputs are 1, and then here all of the inputs are 1 in K. So both of due to these, we'll be having 1s in the output column for K or L, and upper two inputs are both 0 for K and L. Okay, so they should be 0, 0 and 6 1s in the K or L. Any question?
No, sir.
Okay. Okay. Then the second bracket, which is K and not M. We can enlarge this up. K. And as this is a rough working, you can have a dot for the K and not M. Okay, just for the rough working part, just for the rough working part. Not allowed to be written like this in the expression where asked. Okay, K dot not M. So K is this column, not M is this column, and goes if both of the inputs are 1, only then the output will be having 1 if both of the inputs. So we just need to look at this input, and this input is having 1. Then this input is having ones in the both, and then for all these four the K is off. So it doesn't matter is not M is on, it will always be off. Okay, this is how you do it. Zeros in the first four, 0, 0, 0, 0. Then both of the fifth inputs for both the K and not M are 1. So it will be 1, then 0. Then the second last input for both of the K and not M columns are also 1. So, okay, tetra 0, 1, 0, 1, 0. Then ORing them up, OR gate of both of them. The third was OR of both of them. So for the rough working, we can have it as P, we can name it as Q, and so that we can shorten them up P or Q, okay, which is actually K or L or K and not M, okay. So these are the two interested gates or columns right now. OR gate says there will be 1 in the output if any of the columns are, or if any of the inputs are 1. So K or L column is all 1s, 6 ones, and both of the upper rows are zeros for both of the inputs. So it will be same 0, 0, hexa ones. 1, 2, 3, 4, 5, 6. Okay. Then we need to OR it up with the M. This is the or the previous one, and so this whole previous one is single input to the T OR gate. OR gate, the last OR gate labeled as T. This is the single input to that gate. Now it is being ORed with the M. So we can name it as PQ or any PQ, or can we name? Yes, PQR. This is R, and the last column will be R or, okay, I can write it as R or M, which will be T, the T column. Okay. So this is R and this is M. Okay. M is 0, 1, 0, 1 alternates, and this is OR gate. So just instead of the first input, first input, M is 0 for, and this, okay, 0. Why do I think so? I made a mistake. Has anyone identified a mistake?
In the
This
second row, there should be a 1.
in the T column?
There is a 1, actually. I'm sorry.
Okay, okay, okay. We can match it up because I have done it already. We can 0 hepta ones. We can match it up. Let's match it up. No, it is 0 hepta 1. Fine, fine, fine. Already done the circuit. This is 0 hepta 1. We were fine with that circuit. Okay. Meanwhile, it is loading up. Oh, that is opened. It has been opened. Okay, yeah. We have 0 and hepta ones. As I have done it on Friday. Yeah, Friday with grade 10. Okay, there is a question of making an expression from the logic circuit. There is a question of drawing up the truth table, and drawing up means filling up the truth table, finding out the truth of the table. Then there is a question of making a circuit from the expression. Okay, and all of them goes into the last category of, not category of question. We have actually done all the categories. The question number 2, you see in the activity 10.4, the question number 2, and then question number 3. Are you familiar with these questions? Chemical reaction process.
Yeah, I think we've done them before.
Yeah. So what is the first step is to coming up with an expression, expression for, there is the relation for the expression. Okay. One category left, one category left, one category left, and that category is coming up. Okay, look at here. He's trying to prove out that a plus I'm speaking of the part a plus a dot b is equal to a. Oh, is equal to a only. Okay, the second part, the third part, then fourth part. In A levels, you try to practice these category of questions, but not here. But he can ask you if because this is just a activity of performing the truth table. Okay, so find out more on the left hand side, part 1, 2, 3, 4, 5. You should be practicing drawing up the truth table for this format more category of question. Okay, because all of them are, I guess, should be equal, or if not, if you have done the trace perfectly well, then your answer should be, if it is not equal, then it should be not equal. Okay, the last category of question is drawing up the logical expression, making up the logical expression, coming up with the logical expression from the truth, from the truth table. Yeah, this was not before, but it is now. Okay, we'll be doing it on the book. Do not look at the solution if you are having your books opened. We can compare them up. Was it this one, or I should be going for a bit easier one? Okay, this one. Coming up with the Boolean expression, coming up with the Boolean expression from the truth table. We are only interested with the output column, the values in the output column that are ones. Okay, that are ones. That on what conditions of input the circuit gives us the output of 1. Because if it is 0, why are we aren't interested in 0? Because if none of the inputs are available, if everything is off, the power is off, the circuit is off. So we should be only looking at the values in the output column X, which are ones only. Okay, and for the output values 1, we need to trace them up. At what combination of inputs, at what combination of input was it 1? Okay, so the first output, which first output column having 1 is the first row, and this one came on when all of the three inputs were off, when A was off, when B was off, and when C was off. Okay, we cannot argue that can we skip C, can we skip B, can we skip A, can A be 1, can B be something else than 0? No, this is a hard output given to you. This is an output from a circuit in the form of a truth table given to you, and he's asked you to put up a logical or Boolean expression. Okay, so this first output 1 was there when A was off, B was off, and when C was off. And why am I putting so much pressure on this thing? Because there needs to be an AND gate between A, B, and C. AND gate, and because AND is the compulsion, it is compulsory for A to be 0, B to be 0, and compulsory for C to be 0. So that is why we have AND gate in the single row expression. And expression goes like not A. This output was 1. This one came why? Because or this output 1 came on when A was off, not A. And you don't need to underline. I'm just highlighting it that it's mandatory to write and, not B, and not C. So this is the expression only for this output value 1, this one only. Okay. Then for the second value, 1 in the output column X, that is the fourth last row. 1, 2, 3, 4, yeah, fourth last row. This one came on when A was on, B was off, and C was off. This A was on, B was off, and C was off. Is there any question? Question on confusion, A and not B.
No, sir.
And have you done this category of question before?
I think we have. We covered all of the chapter.
Okay. Then the last one, the second last one, which is the last one, came on when A was on, B was on, and C was off. So it is A and B, and not C. Yeah, not C. Okay, now the common sense says, the truth table says that you can have an output of 1 on any of these combination of inputs or on any of these three logical expressions. All the circuits we have seen so far, as an example, this circuit, just above this example, how many outputs and how many inputs to this gate are? There are only two inputs. Two inputs mean positive or negative. Okay. So each expression is just like a negative or positive input. Okay. There is an earth wire. Each expression is an input to a logic gate. There can't be three inputs to a logic gate. There can't be three high voltage inputs to a logic gate. What I'm trying to put that you can have one on any of these Boolean expressions from the circuit, but one at a time. One at a time. You can only try the input sequence combination of first expression. If it gives output, then you can try for the second sequence or combination of inputs from the logic, the second Boolean expression. So this should be OR gate. There should be OR gate between these, which suggests that you can have the output of one from the circuit either on the first expression or on the third expression, okay, or on the second or third expression. So there goes OR gate between these three expressions. You cannot try all of these expressions at once, because, for example, the bottom two expressions says A should be on, A should be on. Okay, fine. But the first expression says A should be off. How can you try all three expressions together? Okay, because students forget where to put and where to put OR gates and they try to cram it. So there should be no cramming. The first one comes on the fixed combination of input, which is not A and not B and not C. There is a compulsion of all these three inputs to be in the same state. Okay, and then once you come up with expressions of multiple ones, then you can say you can have an output of one from the circuit on any of these, but not always, but not of course at the same time, all of them same time tried together. Okay, so there goes the solution from the book. Not A and there's the solution. Not A and not B and not C. Okay, and then how does it put it together? He says if we now join three expressions with an OR gate, we end up with the final logical expression, which is not A and not B and not C, or the second bracket or the third bracket. So there it concludes